Now we will talk about the magnetic quantum number m sub l. So what is the significance of this quantum number? It basically gives us the relative orientation of the angular momentum vector L with respect to an applied magnetic field H, and we see that it is going to be quantized. So the information we get is the relative orientation of the angular momentum, orbital angular momentum vector L with respect to a magnetic field H, and it is quantized. So this one is quantized. As you can see, for p orbitals, L equals 1, p orbitals, we have possible values of m sub L from minus L to plus L, minus 1, 0, and plus 1. If the magnetic field is applied in the z in the positive z direction, you can see that we have three possible values of m sub L and three possible orientations with respect to this magnetic field. M sub L equals to 1 gives us a z component of the angular momentum to be h bar. M sub L equals minus 1 gives z component in minus h bar, or h bar in minus z direction, and m sub L equals to 0 gives no component in the direction in which the magnetic field is applied. So basically we can see that p orbitals exist in three orientations, with three orientations with respect to an applied field. Okay. The other thing is what m sub L gives us is the component of the angular momentum along the field direction. And this is m sub L times h bar. Now we have the magnitude of the angular momentum, square root L plus 1 h bar. So if L is equal to 1, you will see that the magnitude should be square root 2 h bar. And on the other hand, if we look at the z component of the angular momentum magnitude, it is m sub L h bar, and notice that it is less than square root 2 h bar, which is about 1.4 h bar. So it should be smaller because it's a component, and as we can see, it is the case. So one thing we learn is that the angular momentum vector L can never point along the direction of the field, along the field axis. But what it does is it precesses in a cone around the field axis. Okay, so well, this is a little bit counterintuitive if we look at macroscopic objects. So here I would like to put a remark So if you have a macroscopic object, like a spinning top, for a macroscopic object, this L value is very, very large. L is much, much greater than 1. Square root L plus 1 is approximately equal to L. And so that we will see that the object appears to rotate directly around z-axis. So, so that the angular momentum vector is on the z-axis. So, in the case of applying a magnetic field, it's along the field direction or on the field axis. So this seems to be possible for a macroscopic object because you have a very large quantum number, so that square root L plus 1 is approximately equal to L. Okay, so we talked about the significance of the magnetic quantum number m sub L. It tells us the possible relative orientations of the angular momentum vector with respect to an externally applied magnetic field. In the case of p orbitals, where we have L equals 1, for example, there are three possible values, -1, 0, and 1 for m sub L, and that means the z component of the angular momentum, if the applied field is in the z direction, is h bar minus h bar, or 0. So it's m sub L h bar. Since the magnitude square root L plus 1 h bar is always greater than L sub z here, so we can see this. If L is equal to 1, you have square root 2 h bar, which is about 1.4 h bar. That is greater than m sub L h bar. L vector is never pointing along the field axis, but it's precessing in a cone around the field axis with a z component, or a component on the field axis, given by m sub L h bar. But for a macroscopic object, since this quantum number is very large, much greater than 1, square root L plus 1 becomes L h bar, and since m sub L can take values minus L and plus L, it appears that the object's angular momentum vector can be pointing along the field axis.